Hello, welcome to my video on data structures. This is part 4 for the linked list data structure. In this video, we will present the implementation for linked list. Most of the implementations use iterators as part of the interfaces. You can either watch the previous video to learn about iterator or simply treat it as pointers for nodes of the linked list. Let's first look at the overall organization of the linked list class. The private members of the linked list class contain the definition of node, which is defined in line 5 of the code. As we know, each node contains 3 fields: the data content, the prev pointer, and the next pointer. Since we do not expect functions from the other classes to directly interact with nodes, we define node as private. The public members of the linked list class contain the definitions for the nested iterator classes. The Iterator classes serve as interface between external reference of the nodes and the detailed implementation. Hence, they are expected to be called by functions of the other classes. Therefore, the Iterator classes need to be defined as public, as shown in line 8 and 9 of the code. The Iterator class inherits from the const iterator class, allowing the direct use of member functions of the const iterator class without re-implementation. If you are interested in this C++ feature, you can look further into the notion of inheritance. In the linked list data structure, we have 3 private data members. The first data member, the size, records the number of data elements. The head and the tail are the pointers of the sentinel nodes. Recall that they do not store any real data elements. We will also implement the set of linked list operations shown here. While the names of the functions should be self-explanatory, we will discuss the input and output for each function in detail later. Let's start with the operations begin and end. The operation begin returns the iterator that points to the first data element. Recall that the head and the tail nodes are sentinels and they do not store any real data content. Therefore, the first data element should be stored in the node next to the head node. And in line 4, we return the next node of the head. One thing to know that is in line 4, we are actually calling the constructor function of the iterator class, using a node pointer as the parameter to initialize the object. And to do this, we have already implemented the corresponding constructor function in our iterator class. For the end operation, we are actually returning the tail node that does not store any data element. We can see that from line 3 of the code. You may be wondering why the begin operation returns an iterator pointing to actual data element, but the end operation returns an iterator pointing to a sentinel node. The reason is, if we do that, we will be able to use iterators to write for loops in the same fashion as for loops written with index. If you take a look at regular for loops shown in line 5, you will realize that the index I will not take the value of size before the termination of the for loop. Similarly, in line 6, the iterator it will not take the value of end either. It means that if we make the operation end return an iterator for the last data element, then the last data element will always be missed if we write for loops in this way. In short, you can just remember that begin points to real data and end does not. And the reason for the design is just to make the coding style consistent. Now, let's take a look at the search operation. The function takes in the search key as the only parameter and returns the iterator that points to the first occurrence of the search key. If the data does not occur, then the end iterator will be returned. Overall, the implementation is straightforward, where we use a for loop to scan each data element to find the search key. There are just 2 points I want to talk a little bit more. First, in line 5, we declared iterator it with auto type, which indicates that we rely on the compiler to automatically infer the type of it. It is a shortcut of the complete declaration of my linked list subclass iterator that is shown in the comment. Second, in line 8, where we compare the data elements with the search key requires that the double equal operator equals to be defined or overloaded in the data type class. But if we use int as data type here, then it should be fine because we can always use the double equal operator to compare integers. The next one is the insertion operation. We have discussed the high-level idea of insertion in part 2 of the linked list data structure, and here I will just give a brief review. Essentially, we expect to insert data X before location P. In this case, the data element that was originally before P can be represented as P arrow prev. To make the insertion, we need to make 4 pointer changes, which are marked red in the pointer fields. First, we will create a node, say N, which holds the data to be inserted X and has its prev pointer point to P arrow prev and has its next pointer point to P. All of the above can be done using the first line of the code by calling the node constructor function with the 3 types of information as parameters. Second, we need to set the next pointer of P arrow prev to N, which can be done by line 2 of the code. And at last, we will set the prev pointer of P to N, which can be done by line 3. Now, let's take a look at the actual implementation. The insertion function takes in 2 parameters. The first one is itr, the iterator version of P that tells the insertion location. The second parameter X is the data to be inserted. The return value of the function is the iterator for X after it is inserted. In line 5 of the code, we obtain the pointer P using the iterator itr. Lines 6 through 8 handle the creation of the new node and the associated pointer changes, and are exactly the same as we discussed in the previous slide. Line 9 increases the size as a new data element is inserted. And in line 10, we return the iterator that points to X. The next operation is splice, or you can think of it as a more generic merge operation. The function has 4 parameters. The first parameter is the iterator for the splicing or merge location in the current linked list. The second parameter is the linked list from which the splice data elements come from. The third and fourth parameters correspond to the range of the data elements that need to be spliced in. Note that the data element pointed by from will be spliced in, and that pointed by to will not. The return value is the iterator before the splicing location and is similar to the insertion operation. The implementation is also straightforward, as we can simply call the insertion operation in line 7. The only place we need to be careful is in line 8, where we need to specify the object list when erasing the data elements that have been spliced in. In other words, the erase function should be called from the second linked list where the data elements originally come from and not from the current linked list. Let's move on to the erase operation. Basically, we wish to delete the data element pointed by P. In this case, the data element before P can be represented as P arrow prev, and the data element after P can be represented as P arrow next. For erase, we need to change 2 pointers, which are marked red in the pointer fields. First, we need to set the next pointer of P arrow prev to P arrow next, in which case we skip the data element pointed by P. This can be achieved by line 1 of the code. Symmetrically, in line 2, we need to set the prev pointer of P arrow next to P arrow prev, where we also skip data element pointed by P. Here is the code for the erase operation. The only parameter itr corresponds to the iterator for the data element to be deleted. The return value should be the data element next to itr. In line 4, we retrieve the pointer P of the iterator itr. In line 5, we obtain the iterator of the data element next to itr, and it will serve as the return value. In lines 6 through 7, we make the pointer changes as discussed previously. In line 8, we delete the node and collect the memory. In line 9 and 10, we decrease the size of the linked list and return the iterator. The more generic version of the erase operation has two parameters, from and to, which characterize the range of the data elements that need to be deleted. Note that the data element pointed by from will be deleted, while the one pointed by to will not. The implementation is trivial, as we can simply write a for loop and call the single data version of the erase operation to delete each data element. The return value is the iterator to, which is next to the data elements that are deleted. Then we have the push front and push back operations. They try to insert a data element to the beginning or the end of the linked list, respectively. The input parameters for the functions of both the data element need to be inserted, and they are both implemented by calling the single data version of the insert operation. Finally, we have the pop front and pop back operations, which delete the first or the last data element in the linked list, respectively. They are both implemented by calling the single data version of the erase operation. In summary, we have implemented the major linked list operations in this video. In the next video, we will test our implementation to make sure they behave properly. Thanks for watching, and see you in the next video.